The limit of w equals f of z as z tends towards z0 is a number L such that the modulus of f of z minus L can be made as small as we wish by making the modulus of z minus z0 sufficiently small. Let's see a picture of what's going on. Now, our function f maps complex numbers onto numbers w. So this first plane represents all the numbers z, and this second complex plane is the image of all these numbers. We can call it f of z, so each number can be called f of z or w if you like. So obviously I cannot draw a curve to represent this function f because we're mapping from a two-dimensional plane to another two-dimensional plane. Now z0 is some fixed complex number. I'm showing it in this quadrant, but of course I couldn't show it anywhere. And L is the limit as z tends towards z0 of the function f of z. So L is some complex number. What this limit statement says is that the closer some general complex number z is to the fixed complex number z0, then the closer its image f of z will be to L. So we can pick some complex number z that's close to z0. We can pick it anywhere around z0. Let's pick it here. And it's, as you can see, it's quite close. Well, we would expect f of z to be quite close as well. Let's suppose that f of z is here. So we pick any point close to L. And if we pick, say, a second point that's even closer to z0, we will find in general that its image will be closer to L than this point here is. And as z gets closer and closer to z0, then f of z will get closer and closer to L. Now the distance between these two complex numbers is the modulus of z minus z0. You can just consider Pythagoras' theorem if you want to see where this comes from. Just consider the coordinates of these 2 points as if we're dealing with the xy plane. We would get the vertical distance between the 2 points by subtracting the y values, or the imaginary values. We get the horizontal distance between the 2 points by subtracting the x, or real values. Then we use Pythagoras. We square the 2 short sides, sum them, and take the square root. And that's equivalent to getting the difference between the 2 complex numbers. Just subtract the real parts, subtract the imaginary parts, and get the modulus by squaring the sum of the real and imaginary parts. Well, we square the real and imaginary parts and then sum them, then take the square root after we've done the subtraction. We can subtract in any order. This is the same as mod z0 minus z, so we will get some positive real number. Similarly over here, the distance between f of z and L is the modulus of f of z minus L. Here is the epsilon delta definition of the limit of a function. So we imagine any positive number epsilon, no matter how small. For that number we can always find a new number delta, which is also positive, such that whenever the distance between z and z0 is less than delta, then the distance between f of z and L will be less than epsilon. So we could imagine picking a value of epsilon that's extremely small. Say something like this number here, 0.000001. Then we will always be able to find a positive number delta, such that whenever z minus z0 is less than delta, then f of z minus L will be less than this number, 0.000001. So delta will in general be related to epsilon. So delta will be some extremely small number. So we can just pick any number epsilon off the top of our heads, no matter how small. Has to be positive. We will always be able to find a corresponding number delta, which would be probably a similar number, such that whenever the distance between z and z0 is less than this new number delta, the distance between f of z and L will be less than the number epsilon that we chose at the start. So this is a more precise definition, but the intuitive sense that we have, which is that as z gets closer to z0, f of z gets close to L, is good enough. Now z can approach z0 along any path in the plane. So I could go around like this, and as long as the distance between z and z0 approaches 0, If this limit exists, we will find that f of z will approach L, such that the distance between f of z and L is approaching 0, of course. So we can choose any path we like when taking this limit, unlike in the case where we're dealing with functions of a real variable, where say x can only approach, say, x0 from a particular one of two directions, either from the left or from the right. So here x takes the place of z and x0 takes the place of z0, so x0 is some fixed constant number. Now in some cases L is equal to f of z0. So to get this limit, we just calculate the value of f at z0. In that situation, we say that the function f is continuous at the point z0. Here is an example of a continuous function. F of z equals z squared minus z. So if we want the limit of this function as z approaches I, we just calculate f of I. So here z0 is equal to I, and f of z0 is f of I, so we just plug I in for z. So we have I squared minus I, it's minus 1 minus I. Here's another example. Well, we're dealing with the same function again, z squared minus z, but now we're taking the limit of this function as z approaches 2 plus I. So here's the point 2 plus I. This function is actually continuous at all points in the plane, so we could just plug 2 plus I in for z and calculate all of this. And if you do that, you will find that you will get 1 plus 3i. Just to show you that we can take this limit along different paths, we will look at an example here where in the first case we're taking complex number z that lie in this path here, that is on a horizontal line through y equals 1. So the general form of a point on this path is going to be x plus I. So the real part can be any value, but the imaginary part must be plus 1. We calculate f of z, so we just plug x plus I into this. We square it out, we get x squared plus 2xi plus I squared. Well, I squared is minus 1, and then we subtract z, so we subtract x plus I. So we rewrite this, just gather all the terms not involving I together. Those terms constitute the real part of f of z. The imaginary part of f of z comes from the terms that involve I, so that's plus 2x minus 1. Now we want points on this path to approach the complex number 2 plus 1i, and we're approaching it from the right. So we're just considering values of x that are actually greater than 2. So we're letting x tend towards 2 if we're approaching from the right, if x is greater than 2. Although we could approach it from the left actually, if x is less than 2. We'll see that it doesn't actually matter. So if we want z, which is x plus I, to approach the limit z0, which is 2 plus I, we just have to let x approach 2. So we just have to take the limit of this expression here as x approaches 2. Now this is actually a continuous function of x, so we can just plug 2 in for x in this expression here. And if we work out all of this, we will end up getting 1 plus 3i, which is what we will get actually if we just plug in 2 plus I directly into z squared minus z. We could take the limit as z approaches z0 along this vertical path here. Now, what is the equation of this vertical path? Well, the real part is 2. The imaginary part is any value y. Y can be greater than 1 or less than 1. We calculate f of z, so we just plug 2 plus yi into z squared minus z. Next we want z to approach z0. So we want 2 plus yi to approach 2 plus I. Now for that to happen, we just need y to approach 1. So we need to take the limit of this expression here as y tends towards 1. Now since this function is continuous, we can just plug 1 into this. And if we do that, plug in y equals 1, we get 1 plus 3i. As a final example, let's consider a path that's a straight line passing through z0 and the origin. Any complex number on this line can be got by taking a multiple of z0. We could also think of vectors. A vector with its tail at the origin and its head at any point on this line is a multiple of the vector with its tail at the origin and its head at z0. It's just a scalar multiple. So z is any general point on this line. If k equals 1, you can see that z is just equal to z0. If k equals 2, well then z is a point that's twice the distance of z0 from the origin, but it's on the line joining z0 to the origin. Anyway, let's get f of z. So we just plug this in to z squared minus z, work it all out and simplify it here, and we want to take the limit as z approaches z0. To do that, we just let k approach 1. So we take the limit of this expression here as k tends towards 1. Since this is a continuous function of k, we can just plug 1 into this, and again we get 1 plus 3i. Let's look at this example here. F of z is z squared plus z plus 1. We want to take the limit of this function as z approaches 1 plus 2i. Now, this function exists at 1 plus 2i, and this function is also continuous at 1 plus 2i. So the limit of f of z as z tends towards 1 plus 2i is just f of 1 plus 2i. So this is what we get. Let's look at the real part. Well, we have a 1 squared plus 1 plus 1, that's 3. Then we have 2i squared. Well, that's 2i times 2i is 4i squared, that's minus 4. Now let's get the imaginary part. From here, the imaginary part is 4i, and then we have a 2i, so that gives us 6i. So we get minus 1 plus 6i. Okay, to show that this limit is path independent, we have a couple of examples here. The first example is a path parallel to the x-axis coming from the right. So we have complex number z approaching 1 plus I from the right. Well, any complex number on this line has the form x plus 2i. The imaginary part of any complex number on this horizontal line is 2. And the real part is x. Well, if we're coming from the right, x is actually greater than 2. So we need to calculate f of z. Well, that's just f of x plus 2i. So we just plug x plus 2i in for z in our function. We gather up the terms that don't involve I. All those terms constitute the real part. So the real part is x squared minus 4 plus x plus 1. The imaginary part is 4x plus 2. Now we want to calculate this limit, but since we're moving along this path here, as z approaches 1 plus 2i, it's the same thing as letting x approach 1. So we're taking the limit as x approaches 1 of this expression here. Now since this here is a continuous function of x, we can just plug 1 in for x. So we get 1 plus 1 is 2 minus 3 is minus 1, and we get 4 times 1 plus 2 is 6, minus 1 plus 6i. Let's take a second path. This time z is approaching 1 plus 2i along a line parallel to the x-axis. So here's the picture. So z is a point on this line, and real part, as you can see, is 1, but the imaginary part is some general value y. Well, it says z is approaching the point from above, so y here would actually be greater than 1, but it doesn't matter. We could also approach from below, and you know, we're dealing with a continuous function, so from either side we will get the same result. So in this situation here we have to get f of z, where z is 1 plus yi. So let's just see that. So here is 1 plus yi, we plug that in for z. We want to take the limit as z tends towards 1 plus 2i. Well, that's the same thing as letting y tend towards 2. So z is 1 plus yi, so if y tends towards 2, obviously z will tend towards 1 plus 2i, and that's what we want. And since this here is a continuous function of y, we just plug 2 in for y. If you plug 2 in for y here, you'll get 1 minus 4, which is minus 3, plus 2, which is minus 1. And over here, if you plug 2 in, you get 2 2s are 4, plus 2 is 6. So again, we get minus 1 plus 6i. Finally, our path is a line joining the point 1 plus 2i to the origin. So any point on this line has the form k, a constant, a real number, times 1 plus 2i. We explained that in the previous example. So here's our z. So for any real number k, we have a point on this green line. K is negative, we'll have points down here actually. So as before, we have to get f of z, so we just plug this in for z. We want to take the limit as z approaches 1 plus 2i. Well, that's the same thing as taking the limit of this expression here as k approaches 1, because when k approaches 1, we will get z approaching 1 plus 2i. So we just plug 1 in here, we get 1 plus 1 plus 1 is 3, minus 4 is minus 1, and plugging 1 in here, we get 4 plus 2 is 6. Now let's take an example of a function whose limit as z tends towards z0, where z0 is the origin, depends on the path over which we take the limit. Our function is z bar over z, and the path that we will take first of all is along the x-axis, approaching the origin from the right. So let's look at a general point on this path. Well, it's just z equals x plus 0i. We can leave out the 0i. Let's get f of z. Well, we want z bar. Well, the conjugate of x is just x. Its imaginary part is 0, so x plus 0i becomes x minus 0i. And we divide it by itself, by z. So we get x divided by x is 1. So we see that the limit as z tends towards z0 in this example of f of z is just 1. We just get a constant for f of z. F of z equals 1 for all points on this path. So it doesn't matter about taking this limit. We're getting the limit of just a constant, so we just have that the value of the constant, which is 1. Now let's approach z0 along the positive y-axis. So here's our path. So any point on this path here has the form y times I. The real part is 0. So to get fz, we have to get the conjugate of z. Well, the conjugate of y times I is minus y times I. We change the sign of the imaginary part, and we have to divide that by z, which is y times I. The i's cancel, and you see we get minus 1. So now if we take the limit z tends towards 0 of f of z along this blue path here, we are going to get the limit as z tends towards 0 of minus 1. Well, the answer is just going to be minus 1. So we get two different values for this limit, depending on which of these paths we take. So in this situation, we say that this limit does not exist. So for the limit to exist, it has got to exist along all paths. Here is an example of a function that is continuous everywhere, except at the 2 points plus 3i and minus 3i. For a function to be continuous at a point, the value of the function must exist at the point. Now if we calculate f of 3i, we will get 0 in the denominator. We'll get 3i times 3i, that's 9i squared plus 9. Well, that's minus 9 plus 9, which is 0. So we've division by 0. So that means that f of plus 3i does not exist. Neither does f of minus 3i. We'll get another 0 for the denominator. So if the function doesn't exist at that point, then the function is not continuous at that point. In this case, there's only 2 points for which the function is not continuous. As a matter of fact, this function is continuous everywhere else. So if we want to calculate the limit of this function as z approaches I, we just have to calculate f of I. So we see that as z approaches I, f of z approaches 3/8. Let's take this example. F of z equals z divided by z squared plus 4. Now, this function is discontinuous at the values of z that make the denominator 0. So we just set the denominator equal to 0. So we just solve this equation. We get the square root of minus 4. That's the square root of 4 times the square root of minus 1, which is plus or minus 2i. Now, these are actually the only 2 points at which the function is discontinuous. Now, I won't prove that. Next, we want the limit as z tends towards I of f of z. Now, the function is continuous at I. So, to calculate this limit, we just get f of I. We just plug I in for z. And we get 1i over minus 1 plus 4. So that's 1/3 I. So in general, any polynomial in z is continuous everywhere, whilst any rational function is continuous everywhere, except at the zeros of the denominator. So we've just dealt with rational functions. So these two are rational functions. These are continuous everywhere, except at the zeros of the denominator, where z squared plus 9 is 0, or in this case here, where z squared plus 4 is 0.